Okay, guys, welcome. We're going to do topics in precipitation type forecasting, and I'm going to this section, and I went to the print version of this, just kind of easier to go through, and we'll just kind of highlight some of the important things about this. So we started out the lecture, and I said I want you to define certain words, and I want to make sure that you are defining them with respect to what uh, is dealing with in this module. So just don't look up a word and go, that doesn't make any sense with how precipitation forms. Okay, so the very first thing that we have to look at is this diagram. And so I want to kind of explain what is going on with these diagrams. So I'll pull out my trusty Epic pen and I'll get some stuff in here. So here we're talking about a cloud. And in this cloud, we're basically saying, and it doesn't really matter where the cloud base is. There's your LCL. And then we've got this big layer of clouds here. And we're saying that the temperatures as you go higher tend to be cooler. Now, we said when we lift air from the beginning, the temperature is going to drop at dry adiabatic lapse rate. As you go into clouds, there's latent heat being released. And so it's now cooling at a slower rate, which we call the wet adiabatic lapse rate. But it's still getting colder as you go up throughout the atmosphere. That may be true in different ways when we're in clouds that are being forced descent and the atmosphere. We're not going to get into that details. I just want you to kind of look at this cloud is. So we get to a point here where there's a freezing line, and then above it, water exists in liquid form, but it's below freezing. So I want you to write this down. Water freezes at 0 degrees Celsius only when there's a lot of water. So if I had a pond or even just a puddle, there's so many places in that puddle that can turn below to a point where it turns into ice. And then you're going to be able to get that thing to freeze over very rapidly. And we'll explain how that happens in a second. But in a cloud, the droplets are so small, even though it's below freezing, those really, really, really small droplets don't have an opportunity to turn into an ice crystal. And it doesn't happen until I get up here, a little bit higher up in the cloud, and we're going to discuss what that is in a little bit too. So the water that exists in the cloud that's still liquid but below freezing is called supercooled water or supercooled liquid. That's super important. Okay, now when we talk about how clouds are going to behave, this is the idea, an idealized clouds. We're going to start getting over from a cloud that becomes glaciated, meaning you're getting ice crystals forming in it. So if I said there's a cloud that's glaciated, it means that I've got ice. In those words that I gave you to define, I said that a cold type cloud has ice in it. Not everything is ice, and that's going to be super important. But some of the droplets, the cloud droplets, really, really small drops, are turning into crystals. So, but some of them are still super cooled water. That's a cold type cloud. If a cloud is only made of ice, that is a glaciated cloud. That is definitely a cold type cloud. But the whole cloud is said to be glaciated. Here's what I want you to write down. A cloud that is only ice is called cirrus. C-I-R-R-U-S. Cirrus clouds are those high wispy ones. But even on the top of a thunderstorm, we talk about the cirrus anvil. Those are parts of the cloud that have been completely glaciated. All right, now we're going to go a little bit further into this Bergeron-Feen-Dyson process. This was named after these two guys. Alfred Wegener was one. He's the one who did continental drift. But this is a process, and we're going to talk about how ice crystals grow. I want you to write this down. The Bergeron-Feen-Dyson process describes how ice crystals grow at the expense of supercooled water droplets. In other words, ice crystals get bigger and supercooled water droplets get smaller. And the ice crystals are growing because of this process. So what happens here is we have nucleation. Now, nucleation is the turning of liquid into ice. That's what the word nucleate means. So we have two types of nucleation. You should write this down. homogeneous nucleation, and heterogeneous nucleation. And I had you try to define that in those words. And so we'll try to clean that up. But what's really important, whoa, why did that happen? Is to see what's going on. Homogeneous nucleation says, I've got this little super cool water droplet, and the temperatures are really cold. Notice it's 36 degrees below zero, and it's still liquid water. But if it gets cold enough, all of a sudden it turns into an ice crystal. Now I asked you, what's a crystal? A crystal, the most important thing for defining what a crystal is a crystal is six-sided. It's hexagonal. There's a hexagon. So a crystal is hexagonal, six-sided. So if you look here, it's got 1, 2, 3, 4, 5, 6. Not an octagon, 6 sides. That's what makes it a crystal. And here's something that you probably need to know. Supercooled water droplets will all turn into ice, and I'm going to just say at -40. Okay, right here. So any cloud that's below -40 degrees Celsius is going to be only ice in it. Absolutely, only ice. It's completely glaciated. It would be cirrus cloud, okay? And if you've got nothing else to go on to, that's what's going to happen. It says here larger droplets freeze at -36. So here's the larger the droplet, the easier it is to freeze. So when we talk about sleet, sleet is a raindrop that turns into an ice pellet. That's called sleet, S-L-E-E-T. The raindrop itself freezes. It doesn't take much temperatures below freezing to have that happen. Okay? Now, the other type of nucleation, of liquid turning into ice, is called heterogeneous nucleation. In other words, we need something else. This hetero means different, so we need something else of a different sort. Well, what do we need? We need these things called ice-forming nuclei, and you should probably write that down. Now, I'm not going to worry about necessarily the different types, but I want you to see this video here. Boom. And what it's saying is that this supercooled water droplet comes in contact with something. This is an ice nucleus. And an ice nucleus, when it hits or comes in contact with the supercooled water droplet, will make it turn into a crystal. Notice the temperature does not have to be really, really, really cold, not -40 like it was before. So when the ice crystal, or when the water turns into an ice crystal, when it comes in contact with this ice nucleus, that's what we call a heterogeneous nucleation. And that's activating at some -10, -12. We'll show you a little bit more detail coming up in a second. So it says, well, what kind of things do that? Well, leaf bacteria, and it activates. It'll cause nucleation at -2.9. Silver iodide. These are things that you would use for cloud seeding. This kaolinite clay, -9. Common clay. This is out in the atmosphere quite a bit. And some other things. And what they're doing is these are the common ones. What is the most important thing? You write this down. An ice nucleus has a structure similar to ice. Doesn't have to be a perfect crystal, but it has a structure that's similar. And so what we say at that point is we say that there's a lattice, L-A-T-T-I-C-E. And that lattice is saying something about whether or not you're going to get a formation of an ice crystal. If I were to look up here under the term lattice for a garden, and look at the images of that, this is a lattice. Let's see where it is. Come on. Slow enter. See, this is what we call a lattice work. And it's a structure, so things grow onto it, and it gives it a foundation of the structure. So that's what I mean by the word lattice. I don't need all these garden lattices anymore. But that's what's going to happen. When they activate, when they reach a particular temperature below zero, and they start ice formation. Okay? Now, I have a crystal. The crystal is now going to start to grow. How does it grow? Well, the most important thing is this one. In fact, this video is more important than any video to explain the Bergeron-Fien-Dyson process. So what is it doing here? It's saying this. This is your supercooled water droplet. This is your ice crystal. These are vapor molecules. And so the vapor molecules are going straight into ice. You define this word. That's called deposition. So vapor turning directly into ice is called deposition. The supercooled water droplet, on the other hand, is getting smaller because it starts to evaporate. See, they see saturation a little bit differently. This is kind of a confusing, and it took a long time to figure this out. Got my iced coffee. So the liquid water, supercooled water, evaporates. The vapor, excess vapor, goes into the crystal through deposition. So if you wanted to summarize, which I think you need to do right now, the Bergeron-Fien-Dyson process is the ice crystal grows through deposition at the expense of the supercooled water droplet. So watch that video again, see? The supercooled water droplets get smaller, the crystal gets larger, vapor to ice is deposition, liquid to vapor is evaporation. Now, this stuff with vapor pressure, I'm not going to worry about this a whole lot, but the idea is this. Between about -10, and I'm going to go ahead and draw this, between around -10 and about -20, that's where this happens most effectively. And this area, this thing that we talk about, is called the DGZ, which stands for the dendritic growth zone. So that's in this area from about -10 to -20. I think that the module itself says -12 to -16 degrees C. So that's basically what they're saying it is. I'm saying from like -10 to -20, but sort of in the middle. It says optimal growth rates occur near 15 degrees C. So that's where these crystals are going to grow the most effectively. Okay, now, when I say the crystals are growing, I am talking about ice crystal habit. So you want to take a look at this term called the habit. H-A-B-I-T. And that just says, what does the crystal look like? You have columns, you have prisms, you have plates, you have stellar plates, you have needles. You ever seen the snow that falls with little needles, it looks like? Well, the ones that's most effective in producing accumulating snow is this thing called a dendrite. So what you would imagine to be a snowflake, if I said cut out a little piece of paper with make a snowflake, you'd probably think dendrites. Dendrites are the best. The habit of an ice crystal forming a dendrite is what's going to give you the most snow. And the dendritic growth zone says between -12 and -16, that's where deposition growth of the crystal grows the best, and it forms dendrites. So if I have a part of the atmosphere, see if you can write this down. If I have a part of the atmosphere that's saturated between -12 and -16, that's where I get my best profile of temperature to produce snowfall, the dendritic growth zone. So you need to know DGZ. Okay, another way to make the ice crystal grow is this thing called accretion. So accretion is the process, is the name of it. It's growth by accretion. It's called riming. Okay, so what it is ice crystals grow when they collide with supercooled water droplets. Now remember, in heterogeneous nucleation, those ice crystals um, were able to form when it came in contact with something that had an ice-forming nucleus, something that was similar in structure to ice, like a lattice. Well, what's more similar in structure to ice than ice itself? So I've got this crystal falling into supercooled water, and when it does that, that supercooled water will freeze right onto it, and you get growth by accretion. So accretion over here is this video here. These are all supercooled water droplets hitting the crystal. They freeze when they come in contact with it, and it turns into this little snow pellet. Well, you know what you call that? That snow pellet is called graupel. Okay? Snow pellet is called graupel. And I'm going to watch this little bit of a video here with you on what is graupel. And we don't want to hear your...
When you cross the street is a negotiation. It looks like Dippin' Dots falling from the sky.
Dippin' Dots.
Styrofoam packing pellets, but this precip is called graupel. It forms in convective storms, which are the taller clouds like thunderstorms. In fact, that's what they are. You'll usually hear thunder when graupel is falling. Several lightning bolts flashed near Georgetown on Monday, as about an inch of graupel fell before turning to snow. Graupel starts as a snowflake which forms high in the cloud. It then falls through a layer of tiny supercooled water droplets. That means the water is below freezing but still in its liquid form. Those supercooled droplets freeze on contact with the flake, forming a thin layer of rime ice around it. The same rime ice coating gets deposited on things like conifer needles during a freezing fog event on the ground. Graupel forms in all thunderstorms but usually melts into rain before it hits the ground. That's why you usually only see it in the beginning or the end of thunderstorm season. You will sometimes hear it called soft hail or snow pellets, but it's neither hail nor snow. It's kind of a combo. Ice-covered snow, but it's too small and soft to cause any damage. We don't keep graupel stats, but it's a lot more common in Colorado compared to most states. And by the way, it's spelled Graupel. So don't let your smartphones autocorrect the word when you're trying to impress your friends from Texas with a super cool Twitter post. Meteorologist Corey Reppenhagen, 9 News.
Okay, that's awesome. So what do you need to know from that thing? You know that graupel is snow pellets. It is truly snow pellets, but it's like Dippin' Dots. And I think you all know what Dippin' Dots are. So I'm going to use that. If I say, what's the precipitation that looks like Dippin' Dots, you'd say graupel. Graupel is ice crystals that grow through accretion, or what we call riming. And it's soft and kind of spongy, so you can kind of crush it in your hand. Now, this is not to be confused with sleet, which is actually liquid drops that turn into ice. So this is snow pellets. Sleet is ice pellets. And sleet ticks when it hits the ground. So you tick, 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 tick. Hail is much larger, and we're not going to get into that. Hail is only associated with thunderstorms. Now, I'm taping this on April 9th, and we have some showers that are moving through the area. There could be some of you that are experiencing graupel today, so really well-timed lecture on this. Okay. The other way that you can grow an ice crystal is through aggregation. Aggregation is snowflakes sticking to snowflakes. So when snowflakes stick to snowflakes, that's called aggregation. Trying to think. Did I just hear thunder? I may have. We'll see. If something happens, I'll show you the camera outside. Okay, so aggregation, snowflakes sticking to snowflakes. Have you ever seen it like you get these really big, like $half size snowflakes that are falling? Usually what makes snow stick together is it's wet. So when the temperatures are warmer and the snowflakes are melty, they stick together, and that's called aggregation. Okay, so here's some stuff about the habit of them. Here's the dendrites forming in the -12 to -16, the dendritic growth zone. Here's the underlying shape, which is the hexagon, which is important. Now, let's go to this. So for precipitation to grow this way in the Bergeron-Fien-Dyson process, which is dominant, this is why raindrops form. You have a thunderstorm. Thunderstorms start out as snowflakes, always. This is the Bergeron-Fien-Dyson process. So what we're saying, and this is really important that you write this down, in order to get the Bergeron-Fien-Dyson process to go, you need both supercooled water and ice crystals. You need both. The ice crystals grow, supercooled water drop shrinks. So you need both. Well, at about -5 in a cloud, almost all of the cloud is all liquid. If it's all liquid, we call that a warm type cloud. When you get between about -10 and -20, you notice that there's a lot more ice, and that's going to be where your DGZ is. Once you get out here to -25, almost all of the cloud is going to be ice. So these are kind of percentages of how things are going to work. So really important that the clouds, that you understand that clouds are going to grow precipitation the best in this area here, at those ranges. And that's called the DGZ, the dendritic growth zone. Look at this. If the temperatures range between 0 and -4, there's really going to be no initiation. The potential presence of ice initiation at those temperatures, there's just not going to happen. So at 0 to -4, temperatures are going to be cold, below freezing. It'll be super cooled water, but there's really going to be no ice. So that's still a warm type cloud. So can you get a warm type cloud above freezing? You better believe it. You should probably write that last one down. Now, here's the problem. If an airplane flies through a cloud where it's all supercooled water, that water starts to collect on the wing. And as the water collects on the wing, the droplets become larger and larger and larger. They become like a layer of water. Well, the temperatures are below freezing, so that layer of water is much more likely to turn into ice. And so this layer freezes very rapidly. Now, if you've ever seen ice form on your windshield or on a window, or even if you see it in like a puddle, once you get a little ice crystal grow, all of a sudden, all the other molecules line up and form this wonderful crystal. So it grows really fast. So I'm going to show you a little cool video about a water bottle freezing. Okay, so let's go to this guy. This is probably a little bit.
To fly a rocket ship, you need to be.
And I'm tired of you master class people.
No astronaut.
Here we go. Adult supervision. Can you guys do this? Salt lowers the freezing temperature, so you're going to stay as liquid water and won't freeze anything. Now, this way the ice forms and it grows really rapidly. So that's what's going on when you form crystallization, when it all nucleates. I'm not even going to worry about this end. But when you have an airplane flying through it and you start to get ice forming on the wing, that's called icing. Icing changes the aerodynamics of how air goes over the wing, and therefore the wing does not fly well. So huge problem for aviation is when a plane flies through temperatures that are below freezing in a cloud, because there's going to be a lot of supercooled water that will cause icing on the airplane wing. And when you have that, that leads to all sorts of bad things like crashes and death. So icing is a real problem. If you ever been to the airport, and when the temperatures are near the wintertime, even some other times, you have to worry about icing, and so you de-ice the airplane. Once you start getting over here to -15, -20, almost all of it's going to be ice. So when it's -20, you're going to have ice, and then you get colder, it's going to be more and more ice, and it's not as dangerous. So the worst place for an airplane to fly, write this down, is when it's all super cooled water. Okay? I don't need to worry about this, but here you are. Here's what I'm talking about with aviation icing threat. Liquid water, it's all above freezing, no threat. All supercooled water, significant threat. If you have mixed phase, meaning you have both ice and liquid, mixed phase, then that means you have some ice threat. Once you're high enough above -40, where the temperature, I mean below -40 in terms of temperature, but higher in the atmosphere, it's all ice, and then there's no threat. And it just talks a little bit about how satellites can show you that kind of stuff. So that's your basic concept here in this first one, the ice crystal process method. Okay, so hopefully that made some sense to you guys. Review those terms that we have. Let's look at the partial thickness method. And all I want to say is that you've got thickness, and we've done this before. The thickness of the atmosphere is the vertical distance between two isobaric surfaces. I-S-O-B-A-R-I-C, isobaric. So the warmer that air is, the thicker it is. So we've done this before in class. The thicker the warmer, the thinner the colder. The thicker the distance between those isobaric surfaces, the warmer it is, the thinner the colder it is. So we start looking at various layers of the atmosphere, and the most common one, and the one that I want you to know, is this 1,000 to 500 millibar thickness. So we're saying 1,000 millibars near the ground, 500 millibars up here. This layer, if the thickness of this layer is 5,400 meters, then that's the rain snow line. If it's warmer, it's thicker, and that usually means it's going to be rain. If it's thinner, therefore it's colder, that's usually cold enough to produce snow. So that's what we call a critical thickness. It's 1,000 to 500 millibars in this case, 5,400 meters. That's something that you need to write down. That's the critical thickness. Just to give you some idea of how that works, we have some models that we use. And in this model, we will look at critical thickness. And I'm showing you a bunch of critical thickness, and where it's light blue and white is where it's cloudy. The one that I care about is the white line. That's 5,400 meters. So if we look at where that is right now, that's south of us, which means all areas to the north are cold enough to produce snow. And as we go forward in time, we see that it'll start moving back up. It'll be, if we get precipitation this weekend, it'll be rain. But then that comes through. Notice we're probably still going to get precipitation on Monday morning. And that Monday morning precipitation is going to be cold enough to be snow. And we even look at sometimes in the future of this. And I can use, there's a whole bunch of these different values for thickness. I don't care about that for now, but that's kind of what's going on. And then we start getting some more areas of potential snow and colder. So this next couple of weeks for us here, it's going to be pretty lame. Not very nice weather. In fact, let's take a look at the total snow accumulation. And we see areas very close to us. Even Chicago is supposed to get an inch or two of snow next week. So lots of snow in the forecast, and that's because the thickness, the coldness of the average temperature of the atmosphere is going to be pretty sizably, anomalously cold. Okay. From that, we are able to understand what kind of precipitation we're going to get. So one of the things that I want to show you is what's the difference in the profile. So temperature profile, snow, sleet, and freezing rain. And I can look at images for this because this is going to be one that I'm going to test you on. So I'm going to look at this picture here. We'll skip through that. Here. This is the one that I really want you to see. Okay? And what we're saying is here, this is freezing line in the atmosphere as you go higher. Here's the actual temperature profile of the atmosphere. So what we're saying is the air is saturated, there's precipitation falling, and all the temperatures are below freezing. That means the snow crystals that form are going to continue to fall all the way to the ground, and we get snow. When we get here, though, we get a little bit of a warm layer. We have an inversion. So I want you to define inversion. What is a temperature inversion? So make sure you write that down and then go define it. And the inversion says that we've got warm air on top of the colder air. And so snow falls up here in the cloud, and as it goes to this layer, what's it going to do? Well, the temperatures go above freezing, and it's going to melt. Turns into a cold raindrop. But then as it continues down, it gets colder again. So what's that raindrop going to do? The raindrop, which is much bigger than a cloud droplet, 1,000,000 times bigger, will turn back into an ice pellet. And that's what we mean as sleet. Now the last one here is when I've got air, it starts out as snow, and now the deep warm layer, it all melts. It turns into rain. But it's cold right at the ground. Now, it may not be cold enough to cause that drop to turn back into ice. It was too warm, so it's trying to freeze, but it's still too warm yet. So it's still falling as rain, and then when it hits the ground, it goes to freezing rain. Okay? So I'm going to have a little link on here to Jim Cantori's explanation of the difference of what freezing rain does, because I want you to make sure that you watch that and you can take a little note on that as well. Okay, top-down method, I just want to take a look at this here. I'm not worried about this too much. We've already kind of talked about it, but here's something that's going on where I just mentioned to you with the graphs. I hope the one that I showed you might be a little bit easier to understand. Here's some key points to understand that and what it does, but you can go ahead and take a look at this. This one's kind of interesting. If we look at this thing, the rain, the snow falls, it hits temperatures above freezing and it melts. But because it's drying and evaporating, that raindrop starts to cool. It reaches the wet bulb temperature. And so that cooling, because the rain's evaporating, drops the temperature. So what's happening is the temperature starts dropping, the air becomes saturated, and now the snow stays all the way to the ground. So that's kind of a cool way to see how sometimes it starts as rain and then it turns over to all snow as well. So blah, blah, this, that, and the other thing. We don't need to worry about all of this stuff. I'm more concerned with the stuff I'm giving you. Model algorithms, I do not even care about this for you. There is one other thing that I want you to know, and that's called collision and coalescence. Okay? So I go to Wikipedia and they talk a little bit about it. Let me find collision. Okay, it says in warm clouds. So again, if I've got clouds that have no ice crystals, a warm type cloud, the drops fall and then they start running into other drops. So they collide, collision, and they form, two little drops form a bigger drop, coalescence. So here's that word for you to know, the collision and coalescence. And that's raindrops hitting each other and forming a larger drop. It is not as important in mixed phase clouds where the Bergeron-Fien-Dyson process dominates. So if I have a cloud where I've got a cold type clouds and I've got definitely ice crystals in there, the Bergeron process is what's making it. If the raindrops fall and they bump into each other, collide and coalesce, then they're going to make more and more raindrops, and they'll blow apart and make smaller raindrops. This is really important. Collision and coalescence helps the growth of a raindrop, but it doesn't initiate it unless it's in a warm cloud. In a warm cloud, it's so bad at making drops grow big. Here, let me explain something to you. You ever watch the side of your car window when it's raining? Maybe your mom or dad were driving and you're watching the raindrops and they fall down the window. The big drops are the ones that go fastest, and then they hit other drops and get bigger and fall down. And the other ones are just kind of hanging there. So you probably all watched this as a kid. That's collision and coalescence. The big drops are more effective at hitting other drops. In a warm type cloud, they're also small. It takes a long time to do this. So when the rain falls, it doesn't really grow very big. Do you know what we call that? We call that drizzle. So if I've got drizzle drops, which are really small raindrops, that's usually because I've got a warm type cloud. I didn't have the Bergeron-Fien-Dyson process helping out. If the temperatures are below freezing, I hear an airplane. I thought that was thunder. If the temperatures are below freezing, then it tells me that I get freezing drizzle when it hits the ground. So sometimes we get freezing drizzle, sometimes we get freezing fog. Just it turns into ice, it nucleates when it hits something. Okay, so that's collision and coalescence, and I'll be looking for that. But if you want to see more about this, there's all sorts of cool things. Wikipedia, wonderful. I would recommend that you read it. I think it's really awesome. Maybe I could give you extra credit if you took notes on this whole article. It's really good. I might do that. It's worth extra credit, right? Anyway, that's your precipitation topics. So that is the stuff that you need to write, and I'm expecting you to write notes about this, and then I'm going to show you this video, and I want you to go to this video. So I will post that online, and then at the end of the paper, just throw a little, like, again, a small paragraph about what you thought. I think it's a fun video. Okay, that's types of precipitation. That gives you something about it. And those are all the things that I want you to know from them. So really good set of notes. Some of you are doing awesome with great notes. Others of you could probably stand to do a little bit better. But again, you're going to be studying these notes for the test. Okay? So we'll see you guys later.